All right, just continuing our introduction with vectors, which after a while we'll start focusing on three-dimensional vectors, but let's first stick with 2 dimensions. And I have a vector here that's describing the velocity of a ship. And so the vector 30 over 40 represents, you can imagine a point, 30 to the right, 40 up, or in terms of a map, 30 to the west, east, 40 up, whatever direction that is. And so if the velocity is 30 over 40 kilometers per hour, that means every hour the ship travels a net change of 30 kilometers to the east and 40 kilometers north. So I'll visualize that like this. So here's my vector v. And again, this is what the 30 and the 40 represent. All right, those are all kilometers every hour. And so how far will the ship be traveling after 10 hours? Well, to do that, first thing we want to do is find the magnitude of this vector, which is the length of the vector. And so the magnitude of the vector we can find using the Pythagorean theorem, 30 squared plus 40 squared, which conveniently is exactly 50, so 50 kilometers per hour. That is the velocity in a straight line. Every hour it travels 50 kilometers, so simply in 10 hours, just be that times 10, so 500 kilometers in 10 hours. All right, as well, I want to determine what the unit vector is and then state what that value represents. So the unit vector is a vector in the same direction as v, but exactly 1 unit long. This vector is 50 units long. And so the unit vector, we can imagine being 1/50th of this vector, but in the exact same direction. And so that's exactly how we'll find that vector. The unit vector, which is denoted with a little cap on top, is going to be 1/50th, because the magnitude was 50, of the vector we started with. And in general, the unit vector is always just 1 divided by whatever the magnitude is. Although if the magnitude is, never mind, I'm right. And so that said, just to multiply out the scalar, we get 30 over 50, or 3/5 over 4/5, or to decimalize that, 0.6 over 0.8. And that represents every hour. I now know this ship travels 0.6 kilometers to the east and 0.8 kilometers north. That's what that represents. And notice that has a magnitude of exactly 1, which is why it's called the unit vector, 1 unit. All right, for the rest of this, let's take this in the 3-dimensional space, which is not a vast difference, just an extra coordinate. And so a position vector of 1, 1, 1 just represents a point in 3-dimensional space of 1 to the right, 1 up, and 1 on the z-axis, out, however you want to see it. And similarly for this. And so a position vector is just, again, representing a point in 3-dimensional space in this case. So it says AB, this is A, this is B, and so vector AB is a vector that goes from here to here. And so what is that vector? So in this case, all I need to do is realize, okay, it starts here, it ends here. So I want to find the difference between these. And the order matters because it starts at 1, 1, 1, and it ends at 2, 5, negative 4. I want to subtract this minus this. Well, that just got really messy. So in the end, vector AB will simply just be 2 minus 1. Just this minus this. And then 5 minus 1, and negative 4 minus 1. Which obviously is going to be 1, 4, negative 5. So that's vector AB. All right, well, now we got another point. We have point C, which is on this line segment, or it's on this vector AB. But this vector is a line segment in 3-dimensional space. And so we have a point C that's somewhere on it. But not just anywhere. I give this little ratio here of between AC and CB to show where on this point is. So let me just draw a little line. It doesn't really matter how I draw it. I'll draw something like this. All right, so if this is A and this is B, point C is on the line such that the ratio of A to C, so maybe I'll just put a point here for now, is 1 to 2 compared to C to B, which means the distance from here to here is exactly half the distance from there to there. That's what that's saying. Which means if I want to make my diagram a little more to scale, I should probably adjust what that dot is. And so A to C is half the distance from C to B, so I don't know, something roughly like this. So there's point C, which again means the distance from C to B is twice as much. All right, so now where's C? Well, keep in mind we know where A is, it's at 1, 1, 1. And we know where B is, it's at 2, 5, negative 4. So this is between them, but if it was halfway, I would just find half the distances between 1 and 2, between 1 and 5. It's 1/3 of the way. So I want to find 1/3 of the distance between 1 and 2, 1/3 of the distance between 1 and 5, and so on. And so therefore, C must be at 1/3 of the way between 1 and 2. So the difference from here to here is 1. So I want to add an extra third to 1. So 1 plus a third, because we're only going 1/3 of the distance. For the next coordinate, I got to have 3 here. So I start at 1 again. And this time, AB goes from 1 to 5, which is a difference of 4. So I want 1/3 of that 4 distance. So it's going to still go 1 plus 4/3. And finally, from 1 to negative 4. So it's going the other direction. So I'll put plus, but I'm going to add a negative, or I can just subtract a number. The difference from here to here in total is negative 5. I want just 1/3 of that, so plus negative 5/3. Or maybe I'll just subtract 5/3. Keep in mind, if C was exactly halfway in between, we'd be finding the midpoint. It's just the same idea, just not quite as clean. And so making these all, just evaluating these, so we get 4/3, 7/3, and negative 2/3. And again, that just represents a point, your x coordinate, your y coordinate, your z coordinate in 3-dimensional space. And so anytime we see the phrase a position vector, it is essentially, again, just another way of describing a point in 3-dimensional space, its position. All right. I want a vector with a magnitude of 3 in the direction of 2, negative 1, 1. So we have some vector going in this direction in 3-dimensional space, but this vector here surely doesn't have a magnitude of 3. So let's find the magnitude of this. And so if I want to find the magnitude of that, I use the Pythagorean theorem in 3 dimensions. So the square root of 2 squared plus negative 1 squared plus 1 squared, which is root 6. So this here has a magnitude of root 6. I want to have a magnitude of just 3. So one way of doing that is first to shorten this vector here of 2, negative 1, 1, so that it has a magnitude of exactly 1. Right now it has a magnitude of root 6. And we did something similar in the first question where I can just take this vector of 2, negative 1, 1, and multiply it by 1 over root 6. And that there is the unit vector. This vector here has the exact same direction as this, but it has a magnitude of exactly 1. Well, I want a magnitude of exactly 3, so all I need to do is take this and multiply by 3, which means instead of 1 over root 6, I can change this to 3 over root 6. All right, and so number of things I can do. I will say 3 over root 6. If I simplify it, I don't really have to, but it is kind of nice. It is the same as root 6 over 2. It's a little bit of radical simplification, but I never say it had to be simplified. That said, now if I multiply this out, root 6 over 2 times 2 is exactly just root 6, and so on. I get root 6, I get negative root 6 over 2, and I get positive root 6 over 2. So that vector there is in the exact same direction as this vector here, but it has a magnitude of exactly 3. And if you're not sure, you could check. Just use the Pythagorean theorem, and you'll see this vector here has a magnitude of exactly 3. All right, last one. Most abstract, but like everything else here, it doesn't need to be a lot of work. I have 2 vectors here, a and b, and we know the magnitude of a plus k times b is root 2, which means the length of this plus this times some scalar value, k. So let's just focus on that first. A plus kb looks the same as 0, 2, 0 plus k times 0, 1, 1, which is actually quite pleasant. We get 0 plus 0 times k, so 0. We get 2 plus k times 1, so 2 plus k. And we get 0 plus k times 1, so just k. I'm getting really messy today. I'm going to apologize. All right, so this here, this vector here, represents a plus k times b. And we know the magnitude of this is root 2. So let's find the magnitude of this. So the magnitude of this, again, use the Pythagorean theorem, square root of 0 squared, which is clearly a waste of time, plus 2 plus k squared plus k squared. And we know all that equals root 2, which means we don't need to worry about the square roots anymore. And so cleaning up what I have in here, 2 plus k squared, that is 4 plus 4k plus k squared plus another k squared must equal 2. Because again, everything here must equal just 2 because they're both have the square root of the entire left and right side. Cleaning this up, we get a nice simple quadratic equation here. In fact, we get a perfect square. We get k squared plus 2k plus 1 equals 0, which means I can factor this and get the exact same factor twice, k plus 1, which means k equals -1 only. That's the only value for which this will work. So only when this scalar value of k is -1 will a plus k times b have a magnitude of exactly root 2.